Hi folks, so welcome back to another lesson, and this is part two of our magnetic fields, and we are going to concentrate on the second one, applying the right hand grip rule and Fleming's right hand rule. And as I was doing this, I realised I made a wee mistake in the previous lesson's second bullet point, so that's it corrected there. Okay, so a wee reminder to you that magnetic fields are induced when a charge moves through a conductor, and that the direction of this magnetic field is given by the right hand grip rule. And there's some videos on the YouTube channel to show you how to do the right hand grip rule. It's worth practicing it because once you get the hang of it, it's fairly straightforward. A wee note here, which I don't think I explained very well. In my definition here, I've said a magnetic field is induced when a charge moves through a conductor, and you might get confused because I'm starting to talk about things like a current or a flow of charge, etc. Well, if you think about what a current is really a flow of negative charge, isn't it? So if I switch between talking about a particle or a current, just try and bear in mind I'm really talking about the flow of those charges there. So hopefully that clears up some confusion. Now, to represent the flow of this current or these charges, we can use the idea of an arrow. So, for example, if the charge or current was going out of the page, then if the charge was like an arrow, so imagine each charge was like an arrow, it has a head and a tail, then if the charge was coming out of the page towards you, then you would see the head of the arrow, which would look like this dot here. Oppositely, if you were looking at the charge moving away from you, then you would only see this tail of the arrow, so that's why you would see the cross here. And this is how we usually describe it. Charges moving out of the page, charges moving into the page. And using this notation, along with your right hand grip rule, you can then work out the direction of the magnetic field around that charge. So try it just now. Remember, the first one is moving in the way, so point your thumb into the page and you should find that the magnetic field curls around clockwise, and the other one, the magnetic field, the charge, is moving out the way, so the magnetic field will curl anti-clockwise. So make sure you can do that because it is very straightforward once you see how it's done. Moving on, I've made a wee video about how to use Fleming's right hand rule, and I've put that on the YouTube channel. And the key thing is it's FBI, force, magnetic field and current. Now there is a few other rules about using Fleming's right hand rule, and the first one is you have to use your right hand if you're talking about a negative charge. If we've got a positive charge, you've got two options. You can either use your right hand but flip your answer the other way because negatives and positives are opposite of each other. So for example, if you use your right hand for a positive charge and you find the direction is going, or the force is going up the way, then because it's a positive charge, you've got to flip your answer around and it's actually going down the way. So that's one option. The other option is you can use your left hand, and in this case, whatever answer you get will be the correct answer. I generally just use my right hand and then just remember to flip it round at the end. So that way I don't have to remember, is it right hand for negative or positive? So I just know I always use my right hand and I just flip the answer for a positive charge. Now, one interesting thing is Fleming's right hand rule, if you think about how you hold your fingers, all three fingers are always perpendicular to each other. So what that tells us is that if a particle is travelling parallel to a magnetic field, then it can't really experience a force except along that magnetic field line. So if any particle is going in parallel to a magnetic field, it just carries on as if nothing's happening. And there's a very good reason for that, which we'll look at a bit later on. Now, this is a wee reminder for you about the different types of charges that you've come across so far in your physics. So we have things like electrons, protons, alpha particles, beta particles, gamma waves, and neutrons. Now, these last four we're going to come across again when we do radiation, but in case you've forgotten, here are the charges on these particles. So you probably know electrons and protons. Alpha, remember, is actually two positive protons joined together, so the overall charge is positive. Beta is a flow of negative electrons, so they have a negative charge. And gamma waves and neutrons both have a zero charge. So it's important to know the charge of these particles because remember, if it's a negative charge, we can use Fleming's right-hand rule. If it's a positive charge, I would use Fleming's right-hand rule and then flip the answer. If it's got zero charge, do you think the particle would actually experience any force? Hopefully your answer to me is no, because remember in our definition is that it's a charged particle in a magnetic field. So if the particle has no charge, it can't experience any force. I've done a YouTube video on this slide here, but I just want to go over it very quickly with you so you can see how it's working. And first of all, I've changed the actual information here from the YouTube video to the correct one on this one here, so ignore what it says on the YouTube video. And if we're using Fleming's right-hand rule, we can see that the negative charge is going out of the page, so your middle finger is pointing out of the page. The magnetic field is going from right to left, so that means your index finger is pointing to the left and your thumb is moving up the way, so that means the force is acting upwards. And then for the second example, which is the YouTube video, you have your magnetic field going up the way, so your index finger is pointing up the way. Your charge is going into the page, and remember it's a negative charge. And then finally that means your thumb is pointed to the left, so the force acting on the charge is that it's acting on the left hand side. Similarly with this one, again on the YouTube video I've changed, you'll notice that the wording here is different and this is the correct one, so ignore what's on the YouTube video. And just very quickly, we have the charge going down the way, so that means your middle finger is pointing down the way. We have the magnetic field is going into the page, and so that means the force acting on the negative charge is going towards the left hand side. And then the final one, now notice here we've got a positive charge, so I'm going to use Fleming's right hand rule, but then flip the answer because that's what we have to do for positive charges. So again, the charge in this case is moving down the way, so our middle finger is pointed down the way. The magnetic field is coming out of the page, it's a bit awkward because my index finger is pointing out of the screen, and that means the thumb is pointing to the right, but because it's a positive charge, we're going to flip the answer to the opposite side, so it means the force is actually going towards the left. So have a go at those, see if you can get the hang of it. Once you do, it's actually fairly straightforward. Finally, for our last example, let's look at a past paper question. So it says, an electron enters a region of uniform magnetic field as shown, and they also very kindly tell you the magnetic field is going out of the page. So straight away, if we use our Fleming's right-hand rule, we know that our index finger is pointing out of the page. We're told it's an electron and it's coming in from the left to the right, so our middle finger will point to the right, and the index finger, remember, is pointing out the way, out of the page, so that means the force acting on the electron is it pushes it up the way, or, according to the answer at the bottom, towards the top of the page. So that's an example of how you may be asked to use Fleming's right-hand rule. Now, why do we talk about this? Well, if a moving charged particle in a magnetic field will experience a force, then this is how we build particle colliders. And if we were in class, I would show you this deflection tube and show you how we can actually change the direction of the beam by using a magnetic field. So hopefully when we get back, I'll get a chance to show that to you.